April 26, 1945, dawned gray and foreboding over the waters off Borneo as Lieutenant Commander James Morrison adjusted his oxygen mask inside the cockpit of his consolidated PBY privateer. 23,000 feet below, the emerald waters of the South China Sea concealed what American intelligence believed to be a small flotilla of Japanese cargo vessels attempting to resupply their dwindling forces in the Dutch East Indies. Morrison had no idea he was about to make history. Suspended beneath each wing of his modified patrol bomber hung something that looked like a metallic bat, 12 feet long, with swept wings that gave it an almost organic appearance. The ASMN-2 bat missile, as it was officially designated, represented 3 years of desperate American innovation. Unlike anything the Japanese had encountered, this weapon carried within its nose cone a revolutionary active radar seeker that could hunt ships across 20 miles of ocean without any guidance from its launching aircraft. The development of this remarkable weapon had begun in 1942, when the National Bureau of Standards partnered with the Massachusetts Institute of Technology to create America's first operational guided missile. Dr. Carl Norden's team, working under intense secrecy at the Bureau's facilities, had managed to miniaturize radar technology to fit inside a weapon small enough to be carried by patrol aircraft. The result was a 1,000-pound warhead that could think for itself. Morrison's squadron, Patrol Bombing Squadron 109, had been training with these weapons for months at Eglin Field in Florida. The pilots had nicknamed them thinking bombs because of their ability to adjust course mid-flight, something that seemed almost supernatural to aviators accustomed to dropping conventional ordnance that followed predictable ballistic paths. The training had been rigorous and secretive. Even the maintenance crews were not fully briefed on the weapon's capabilities. As the privateer droned southward through the tropical morning, Morrison reviewed his briefing notes one final time. The Japanese vessels below were reportedly a merchant convoy protected by at least 2 destroyers, making a conventional bombing approach extremely hazardous. The bat missiles would allow him to attack from beyond the range of enemy anti-aircraft fire, releasing the weapons at maximum altitude and letting their internal guidance systems do the rest. What made this moment particularly significant was that the Japanese Navy had no knowledge of America's breakthrough in guided munitions technology. Their ships below continued their northward journey, their lookouts scanning the skies for the familiar sight of American dive bombers that would announce their presence long before any attack could commence. They had no reason to suspect that death was already locked onto their radar signatures from an aircraft they could neither see nor hear. The irony was not lost on Morrison that while American scientists had been perfecting radar-guided weapons, their Japanese counterparts had been pursuing parallel research. The Keigo missile project, Japan's own attempt at creating a guided weapon, utilized infrared-seeking technology but had never progressed beyond prototype stage. Japanese military doctrine still relied heavily on kamikaze attacks and conventional bombing, leaving them woefully unprepared for the technological revolution occurring in American weapons laboratories. As his navigator announced they were approaching the release point, Morrison felt the weight of history settling on his shoulders. The age of precision warfare was about to begin, and he would fire its opening S-hot. Inside the cramped confines of the bat missile's nose cone, a technological marvel barely larger than a briefcase hummed with electronic life. The AN/APS-20 radar unit, weighing just 60 pounds, represented the cutting edge of American miniaturization technology. Its rotating antenna, no bigger than a dinner plate, swept back and forth in a predetermined pattern, painting electronic pictures of the ocean surface below with invisible radio waves. Commander Robert Stevens, the project's chief electronics officer, had spent countless hours at the Patuxent River Naval Air Station explaining to skeptical pilots how their new weapon could literally see its target. A case where accuracy depended entirely on human skill and favorable weather conditions. The bat's radar operated on a frequency of 3,000 megahertz, generating a narrow beam that could distinguish between the metallic signature of a warship and the natural clutter of ocean waves. The missile's guidance system relied on a principle called semi-active radar homing, though the bat represented an evolution to fully active guidance. unlike earlier experimental weapons that required continuous illumination from the launching aircraft. The Bat carried its own radar transom, ITER and receiver, making it completely autonomous once released. This independence was crucial for operational success, as it allowed the launching aircraft to turn away immediately after release, avoiding enemy defensive fire. The electronic brain controlling the weapon consisted of vacuum tubes, mechanical gyroscopes, and servo motors that translated radar information into flight control commands. When the radar detected a target signature matching predetermined parameters, the distinctive rada, or cross-section of a large vessel, the guidance system would lock onto that signal and begin steering the missile toward its source. The entire process occurred without human intervention, representing humanity's first attempt to delegate life and death decisions to machines. Dr. Elizabeth Hartwell, one of the few women involved in the project, had worked tirelessly to solve the problem of target discrimination. Early tests had shown an alarming tendency for the weapons to lock onto friendly vessels or even large waves during rough weather. Her team developed algo, rhythms that could differentiate between the sharp, angular radar returns of constructed vessels and the softer, more irregular signatures of natural phenomena. This breakthrough had been essential to making the weapon combat-ready. The manufacturing process for these electronic marvels took place at carefully guarded facilities across the American Midwest. Western Electric, Radio Corporation of America, and other leading electronics companies had retooled entire production lines to produce the specialized components required for the Bat's guidance system. Each missile required nearly 500 individual electronic parts, all manufactured to tolerances that pushed the boundaries of available technology. According to declassified documents from the Smithsonian National Air and Space Museum, the Bat missile represented the world's first operational guided missile that functioned completely independently after launch. The weapon's development cost had exceeded $50 million, an enormous sum for wartime research. But the potential to strike enemy vessels from previously impossible ranges justified the investment. Quality control testing occurred at the Naval Weapons Center in California, where each guidance unit underwent extensive calibration before installation in operational missiles. The testing process revealed that early production models suffered from a 15% failure rate, primarily due to the fragility of vacuum tube electronics when subjected to the violent acceleration forces of launch and high-speed flight. As Morrison's privateer approached the release point, the electronic minds of two Bat missiles were already beginning their pre-launch sequence, gyroscopes spinning up to operational speed and radar systems conducting final self-diagnostic checks before awakening to hunt their prey. Lieutenant Hiroshi Nakamura stood on the bridge wing of the destroyer Kasumi, his binoculars estowed by, eeping the horizon in mechanical patterns that had become second nature during his 4 years of Pacific combat. The morning sun cast long shadows across the water, creating a mosaic of light and dark that could easily conceal approaching enemy aircraft. His vessel, along with her sister ship Ushio, formed a protective screen for 3 heavily laden cargo vessels carrying desperately needed supplies to Japanese garrisons throughout the Dutch East Indies. The Japanese naval officer had survived the battles of the Philippine Sea, Leyte Gulf, and the devastating American bombing campaigns that had reduced Japan's merchant marine to a fraction of its former strength. He understood better than most that every supply run now carried the weight of survival for thousands of isolated Japanese soldiers. The cargo holds of the ships under his protection contained rice, ammunition, medical supplies, and replacement parts for equipment that could no longer be manufactured in Japan's bomb-ravaged industrial cities. Nakamura's radar operator, Petty Officer Yamamoto, reported clear screens in all directions. The Type 22 surface search radar installed on the Kasumi could detect aircraft at ranges up to 60 miles under ideal conditions, but the tropical atmosphere often created falsy echoes and blind spots that enemy pilots had learned to exploit. Japanese radar technology, while adequate for its time, lacked the sophisticated signal processing capabilities that American scientists had developed during their intensive wartime research programs. What Nakamura could not know was that his radar was already being probed by signals from an entirely new class of weapon. The Bat missiles hanging beneath Morrison's privateer were conducting their own electronic reconnaissance. their active radar seekers sweeping the ocean surface for targets matching their programmed parameters. The frequency separation between Japanese radar systems and American missile guidance allowed both to operate simultaneously without mutual interference, creating a deadly game of electronic blindness. The Japanese Navy's defensive doctrine relied heavily on early warning, followed by aggressive fighter interception, or concentrated anti-aircraft fire from surface vessels. Their combat experience had taught them to expect American attack patterns involving high-altitude bombing, followed by diving attacks or low-level torpedo runs. The concept of a weapon that could be released from beyond visual range and guide itself to target fell completely outside their tactical understanding. Captain Tetsuo Yamashita, commanding the small convoy from his position on the bridge of the cargo vessel Kongo Maru, had ordered radio silence to avoid detection by American submarine patrols. His ships maintained strict blackout procedures even during daylight hours, with all unnecessary electronic emissions minimized to reduce their electromagnetic signature. These precautions, effective against conventional threats, provided no protection against weapons specifically designed to home in on the radar reflections of large metal objects. The Japanese had their own guided weapon program, the Keigo missile project, but development had been hampered by material shortages and the disruption of research facilities by American bombing raids. Unlike the American approach of using radar guidance, Japanese engineers had focused on infrared homing systems that could track the heat signatures of enemy vessels. This technology, while promising, remained in experimental stages and would never see operational deployment. Nakamura's lookouts maintained their vigilant watch, scanning sectors of sky with trained eyes that could spot aircraft at remarkable distances. Their visual acuity, developed through years of Pacific combat, represented one of the Japanese Navy's most reliable defense systems. However, the approaching American privateer remained far beyond visual range, a silver speck against the morning sky that no human eye could detect at such extreme altitude and distance. As the minutes ticked by, the Japanese convoy continued its northward course at a steady 12 knots. Unaware that electronic eyes were already measuring their precise position and calculating intercept vectors for weapons, unlike anything the world had ever seen. 23,000 feet above the South China Sea, Lieutenant Commander Morrison received the final confirmation from his radar operator that hostile vessels had been positively identified below. The briefing back at base had emphasized the critical importance of target verification. American eye intelligence had suffered embarrassing incidents earlier in the war when friendly vessels had been mistaken for enemy shipping. The distinctive radar signatures displayed on his scope matched perfectly with the profile's Japanese naval vessels, confirming that his weapons would find legitimate military targets. Master Sergeant William Bill Crawford, the weapons system operator aboard Morrison's privateer, initiated the final arming sequence for both Bat missiles. The process required him to flip a series of guarded switches that activated the missile's internal power supplies and brought their guidance stems to full operational status. A green light on his control panel indicated that both weapons had completed their self-diagnostic routines and were ready for release. The entire pre-launch sequence had taken less than 3 minutes, far faster than the preparation time required for conventional bombing attacks. The mathematical precision required for successful missile deployment had been calculated by teams of engineers using mechanical computers at the Naval Weapons Center. Launch parameters included aircraft altitude, airspeed, wind conditions, target bearing, and estimated enemy course, and speed. Unlike conventional bombs that followed predictable ballistic trajectories, the Bat missiles could adjust their flight paths continuously, compensating for changes in target movement or unexpected weather conditions. Morrison's bombardier, Lieutenant Thomas Anderson, watched through his Norden bomb sight as the Japanese vessels below continued their formation sailing, completely unaware of the technological revolution about to unfold above them. The ships appeared as tiny dark specks against the blue-green water, their wakes creating characteristic V-shaped patterns that confirmed their northward movement. At this extreme altitude, the enemy vessels seemed almost toy-like, their actual size and destructive potential diminished by distance and perspective. The first Bat missile separated from its underwing mounting point with mechanical precision, its control surfaces immediately responding to commands from the internal autopilot system. The weapon's radar Kir activated automatically upon release, beginning its systematic search for targets within its forward hemisphere. The missile's 12-foot wingspan gave it excellent gliding characteristics, allowing it to cover tremendous distances while gradually descending toward its intended victims below. 15 seconds later, the second missile followed its companion into the morning air, both weapons now functioning as completely autonomous hunting machines. Their radar guidance systems had locked onto the largest radar signatures in their search area, the Japanese destroyer Kasumi and the cargo vessel Kongo Maru. The electronic calculations required for intercept were being performed continuously by mechanical analog computers that represented the pinnacle of available technology. Morrison immediately initiated a sharp left turn, his privateer banking away from the target area to avoid potential retaliation from enemy fighters or anti-aircraft fire. Standard operating procedure required launching aircraft to clear the area rapidly after weapon release, both to avoid enemy response and to prevent inadvertent interference with missile guidance systems. The pilot's job was now complete. The success or failure of the attack rested entirely with the electronic brains of the descending weapons. Below, the Japanese vessels continued their steady progress through waters that had become a technological battleground between competing philosophies of naval warfare. The age of human-controlled combat was giving way to an era where machines would make increasingly complex decisions about life and death. The Bat missiles descending through the tropical air at 200 miles per hour represented humanity's first tentative step into a future where warfare would be dominated by guided precision weapons. As the minutes passed, the missiles adjusted their flight paths with mechanical determination, their radar seekers painting increasingly detailed pictures of their intended targets. The Japanese vessels below remained blissfully unaware that they were being stalked by weapons that could think, weapons that could see, and weapons that would not miss. The first Bat missile descended through 15,000 feet of tropical air, its internal radar painting increasingly detailed pictures of the Japanese convoy below. The weapon's guidance system had achieved positive lock-on with the destroyer Kasumi, the largest and most clearly defined radar signature in its search pattern. The missile's analog computer continuously calculated range, bearing, and intercept vectors while mechanical servos made minute adjustments to its flight control surfaces. Inside the missile's cramped electronics bay, vacuum tubes glowed with electronic fire as complex circuits processed the reflected radar signals bouncing off the enemy destroyer's steel hull. The weapon's guidance logic had been programmed to prioritize military targets over merchant vessels, and the distinctive radar cross-section of the Japanese warship triggered automatic target selection algorithms. Every second brought refinement to the intercept calculation, as the missile's speed and the target's movement created an ever-changing geometric puzzle. The second Bat missile, following a parallel course 500 yards to the east, had locked onto the cargo vessel Kongo Maru. Its guidance system identified the merchant ship's large superstructure and broad beam as an ideal target for a guided weapon attack. The missile's radar could distinguish between the sharp angles of constructed vessels and the irregular patterns of ocean waves, a technological achievement that had required months of testing and refinement at American weapons laboratories. Lieutenant Colonel David Mackenzie, observing the test from a chase aircraft flying at safe distance, watched through powerful binoculars as the two missiles continued their relentless descent toward the UN-suspecting Japanese vessels. As the program's senior test officer, Mackenzie had witnessed dozens of developmental flights, but this represented the first combat deployment of guided missile technology. The success or failure of this attack would determine whether America's massive investment in guided weapons would prove worthwhile. The Bat missile's radar guidance operated on principles that would later become standard in anti-ship cruise missiles throughout the Cold War era. Their active radar seekers transmitted continuous waves of radio energy, measuring the time required for reflections to return from target surfaces. Changes in return signal strength and timing allowed the guidance computer to determine not only target position, but also relative motion, enabling precise intercept calculations that no human bombardier could match. Unknown to the Americans, Japanese radio intercept stations on nearby islands had detected unusual radar transmissions from their general direction, but intelligence analysts had no framework for understanding what they were observing. The signals were too brief and too focused to represent normal aircraft search radar, yet too powerful and too directional to be electronic warfare jamming. Japanese radio operators dutifully recorded the transmissions, but filed them as unexplained anomalies rather than evidence of incoming guided weapons. The missiles had now descended to 8,000 feet, their gliding flight providing an optimal balance between range extension and terminal accuracy. The weapons radar seekers had refined their target lock to the point where individual details of their prey became electronically visible. The destroyer Kasumi's main gun turrets, superstructure, and even her anchor chains created distinct radar signatures that the missile's guidance system processed with mechanical precision. Dr. Helen Morrison, the chief electronics engineer responsible for the BAT's target discrimination algorithms, had spent 18 months developing the mathematical formulas that allowed the WEPO-N to distinguish between legitimate targets and radar decoys. Her work had been inspired by early concerns that Japanese forces might attempt to confuse American guided weapons by deploying metallic chaff or constructing false targets designed to attract missile attacks away from valuable vessels. According to technical documentation from the National Bureau of Standards, the BAT missile's guidance accuracy exceeded all expectations during developmental testing. The weapon consistently achieved impact points within 50 feet of designated aim points, a precision level that surpassed even the most skilled human bombardiers operating under ideal conditions. This accuracy advantage became even more pronounced during combat conditions, where enemy defensive fire and adverse weather often degraded human performance significantly. As the missiles passed through 5,000 feet altitude, their electronic minds began final approach calculations, preparing to deliver their 1,000-pound warheads with surgical precision against targets that remained completely unaware of their approaching destruction. Petty Officer Yamamoto aboard the destroyer Kasumi completed another routine sweep with his Type 22 radar, the green scope displaying the familiar clutter of wave returns and ATM, ospheric interference that characterized tropical maritime operations. His training had taught him to look for the distinctive signatures of approaching aircraft, strong, rapidly moving contacts that would announce enemy attack formations while still at safe defensive distances. The concept of weapons small enough to evade radar detection while maintaining their own guidance systems lay completely outside his experience. The Japanese radar operator adjusted his equipment sensitivity settings to minimize false returns from heavy sea states, unknowingly reducing his system's ability to detect the small, fast-moving contacts now approaching from high altitude. The BAT missiles presented radar cross-sections are ugly equivalent to large seabirds, a signature easily dismissed as biological clutter by operators focused on detecting massive formations of American bombers. Captain Yamashita on the bridge of the Congo Maru observed his escort vessels through binoculars, noting with satisfaction that both destroyers maintained perfect station-keeping despite the challenging sea conditions. His cargo holds contained enough supplies to sustain Japanese gari, isons throughout the Dutch East Indies for 3 months, making this convoy's safe arrival crucial to maintaining resistance against advancing Allied forces. The captain had no way of knowing that his ship had been electronically selected for destruction by a weapon that could see through darkness, weather, and deception. The first BAT missile, now descending through 3,000 feet, had achieved what its designers called terminal guidance lock. The weapon's radar seeker had refined its target picture to the point where it could distinguish individual features of the destroyer Kasumi's superstructure. The missile's guidance computer had calculated that impact would occur in approximately 45 seconds, and mechanical systems began preparing the 1,000-pound warhead for detonation upon contact. Lieutenant Nakamura, maintaining his vigilant watch from the Kasumi's bridge wing, noticed a flock of seabirds circling in the distance and automatically adjusted his binocular focus to examine them more closely. His experienced eye could distinguish between natural bird behavior, and the artificial patterns created by enemy aircraft attempting to use low-altitude approaches for surprise attacks. The birds appeared to be following normal feeding patterns, presenting no cause for concern to a naval officer whose survival had depended on recognizing subtle signs of approaching danger. What Nakamura could not see were two metallic objects descending through the morning air at over 200 miles per hour. Their swept wings and streamlined fuselages designed to minimize radar reflection while maximizing aerodynamic efficiency. The Bat missiles had been painted in non-reflective gray schemes that rendered them nearly invisible against the cloudy tropical sky, even to observers who might look directly at their flight paths. The second missile, tracking toward the Congo Maru, had encountered a brief guidance anomaly when its radar seeker momentarily locked onto a large wave crest that presented an unusually strong return signal. However, the weapon's target discrimination algorithms quickly rejected the false CT and reacquired the merchant vessel's distinctive radar signature. This type of guidance sophistication had required extensive testing against mock targets and environmental conditions that might confuse less sophisticated homing systems. Radio intercept equipment aboard the Japanese vessels continued to detect occasional radar transmissions from unknown sources, but the signals were too brief and too intermittent to trigger defensive alerts. Japanese communications personnel had been trained to recognize the characteristic patterns of American search radars and fire control systems, but the Bat missile's guidance radars operated on different frequencies and used different pulse patterns than any previously encountered American equipment. Commander Stevens, monitoring the attack from his position at the Naval Communications Center on Mindoro, received continuous telemetry updates from Morrison's privateer regarding missile performance and target tracking. The data indicated both weapons were performing within design parameters and appeared likely to achieve successful intercepts. This real-time monitoring capability represented another technological breakthrough that would prove invaluable for future guided weapon development programs. As the missiles entered their final approach phase, passing through 1,500 feet altitude with impact, now less than 20 seconds away, the Japanese vessels below continued their northward course in complete ignorance of the technological revolution about to unfold around them. The destroyer Kasumi's lookouts maintained their disciplined watch patterns, scanning assigned sectors of sky and sea with eyes trained to detect the slightest anomaly that might indicate approaching danger. Seaman First Class Kenji Sato, positioned in the ship's forward lookout station, swept his Beano, colors across the southeastern quadrant where intelligence reports had suggested American patrol aircraft might be operating. His vision, sharpened by years of combat experience, could distinguish aircraft silhouettes at remarkable distances under favorable conditions. What Sato could not detect was the first Bat missile, now less than 800 feet above the water and descending at a 45-degree angle directly toward his ship. The weapon had achieved what modern military analysts would later term terminal attack geometry, with its guidance stem locked immutably onto the destroyer's radar signature. The missile's mechanical brain had calculated impact point, timing, and warhead detonation sequence with inhuman precision. Lieutenant Nakamura, standing beside the ship's captain on Kasumi's bridge, noticed his radar operator gesturing frantically at his scope. Petty Officer Yamamoto had detected two small, fast-moving contacts approaching from high altitude, but their size and speed characteristics fell outside normal parameters for known aircraft types. The contacts appeared and disappeared on successive radar sweeps, creating uncertainty about their nature and intent. Japanese radar doctrine had no classification system for guided weapons, leaving operators without proper procedures for reporting such contacts. The second Bat missile, tracking toward the cargo vessel Congo Maru, had refined its target picture to extraordinary resolution. The weapon's radar could now distinguish between the ship's superstructure, go-handling equipment, and even the wake pattern created by her passage through the water. This level of target discrimination represented a quantum leap beyond conventional bombing accuracy, where human bombardiers relied on visual identification of large target features under often adverse conditions. Captain Yamashita received an urgent message from his radio operator, reporting unusual radar transmissions detected by several ships in the convoy. The signals were too powerful to originate from typical aircraft equipment, yet too focused and directional to represent electronic warfare jamming attempts. Japanese naval intelligence had no existing framework for understanding active radar guidance systems, leaving commanding officers without proper context for evaluating the threat these signals represented. At precisely 10:27 hours local time, the first Bat missile struck the destroyer Kasumi amidships, its 1,000-pound warhead detonating with devastating effect against the vessel's thin armor plating. The explosion tore through the ship's engineering spaces, severing steam lines and rupturing fuel tanks in a chain reaction of secondary detonations that would prove fatal to the 40-year-old destroyer. Lieutenant Nakamura, standing on the bridge wing when the missile struck, was killed instantly by blast fragments that penetrated the bridge structure. 18 seconds later, the second missile impacted the Congo Maru's forward cargo hold, the detonation igniting stored ammunition that had been destined for Japanese garrisons throughout the Dutch East Indies. The resulting explosion lifted the merchant vessel's bow section completely out of the water before breaking her back and sending her to the bottom within 4 minutes. Captain Yamashita survived long enough to order abandon ship, but the rapid sinking prevented organized evacuation of most crew members. The remaining Japanese vessels, suddenly confronted with evidence of a completely new type of warfare, attempted emergency evasive maneuvers, while their radio operators transmitted frantic damage reports to naval headquarters. The destroyer Ushio began launching depth charges rando, falsi into the water, her captain assuming the attacks had originated from previously undetected American submarines. Japanese naval doctrine had no provision for defense against guided weapons launched from aircraft operating beyond visual range. Lieutenant Commander Morrison, monitoring radio transmissions from his privateer now 40 miles from the target area, received confirmation that both missiles had achieved successful intercepts. The pilot experienced a mixture of professional satisfaction and sobering realization that he had just participated in the opening engagement of a new era in naval warfare. The age of precision-guided weapons had officially begun, fundamentally altering the relationship between offensive capability and defensive preparations. According to classified after-action reports later filed with the Chief of Naval Operations, the successful combat deployment of radar-guided missiles represented a technological milestone comparable to the introductio N of naval aviation or submarine warfare. The Japanese Navy's inability to detect, track, or defend against these weapons highlighted the growing importance of electronic superiority in modern military operations, a lesson that would influence naval development throughout the remainder of the 20th century. The waters off Borneo had become quiet again by noon, marked only by debris fields and oil slicks that testified to the revolutionary engagement that had occurred just hours earlier. American search and rescue aircraft, launched from bases in the Philippines, circled overhead documenting the destruction, while Japanese survivors clung to life rafts in the tropical heat. The successful combat debut of guided missile technology had been achieved with a precision that exceeded even the most optimistic projections of American weapons developers. Admiral Chester Nimitz received the preliminary battle report at his Pearl Harbor headquarters within 6 hours of the attack. The message transmitted through secure communications channels that emphasized the classified nature of the new weapon system. The admiral immediately recognized the strategic implications of radar-guided missiles, understanding that American naval forces had gained a decisive technological advantage that could fundamentally alter the balance of power in the Pacific theater. Dr. Carl Norden, the scientist whose team had developed the BATS guidance system, learned of the successful combat employment while working late in his laboratory at the National Bureau of Standards. The NUWs brought both professional vindication and profound concern about the implications of weapons that could kill without direct human control. The ethical questions surrounding autonomous weapons would continue to challenge military philosophers and policymakers for decades to come. Japanese naval intelligence analyzing survivor reports and radio intercepts from the Borneo engagement struggled to understand how American forces had achieved such devastating accuracy from extreme range without any apparent preliminary reconnaissance. Initial theories suggested the involvement of submarine-launched torpedoes or previously unknown LNG-range artillery systems. The concept of self-guiding aerial weapons fell so far outside existing Japanese tactical doctrine that accurate assessment proved impossible. The production facilities manufacturing Bat missiles received immediate orders to accelerate production schedules, with military planners recognizing the potential to revolutionize American offensive capabilities throughout the Pacific Campaign. Assembly lines at Western Electric and Radio Corporation of America began operating around the clock to meet demand for the sophisticated guidance systems that had proven their worth in combat. By war's end, approximately 2,600 Bat missiles would be manufactured, though relatively few would see actual combat employment. Commander Stevens, reviewing technical telemetry from the successful attack, identified several areas where missile performance could be improved for future engagements. The weapons had functioned flawlessly under ideal conditions, but operational testing revealed potential vulnerabilities to electronic countermeasures and adverse weather conditions that would require design modifications. These lessons learned would directly influence the development of next-generation guided weapons throughout the Cold War era. The psychological impact on Japanese naval personnel proved as significant as the physical destruction achieved by the missiles themselves. Survivor interviews revealed widespread demoralization caused by the realization that American technology had achieved capabilities that Japanese forces could neither replicate nor effectively counter. The traditional Japanese emphasis on spiritual strength and tactical innovation seemed inadequate when confronted with weapons that combined overwhelming technological superiority with precision accuracy. According to documentation preserved at the Smithsonian National Air and Space Museum, the April 1945 engagement off Borneo marked the beginning of the guided missile age in naval warfare. The successful employment of radar homing weapons against unsuspecting targets demonstrated principles that would later be refined in anti-ship cruise missiles, surface-to-air defensive systems, and precision-guided munitions that would dominate military technology throughout the latter half of the 20th century. Lieutenant Commander Morrison returned to his base at Mindoro that evening, his aircraft and crew having participated in a historic milestone that would influence military development for generations to come. The pilot's logbook entry for the mission was characteristically understated, noting simply successful ordnance delivery against enemy shipping, without reference to the technological revolution he had helped initiate. The age of thinking weapons had begun. Launched from 23,000 feet above the South China Sea on a clear April morning, when the future of warfare changed forever, leaving Japanese naval forces completely unprepared for the electronic hunters that could see, think, and kill with mechanical precision from ranges previously thought impossible.